Hello everyone, my name is Daria and this is my video for Lab 3 Magnetic Field of Permanent Magnetic Dipoles. The purpose of this lab is to explore the magnetic field produced by a bar magnet and to understand the distance dependence on magnetic field from a particular source, which is in our case a bar magnet. In order to perform desired measurements and experiments, I used a mobile app that measures magnetic field, a bar magnet, a piece of tape, and a ruler. Additionally, we used closed group model to compare our results. Before we discuss main results, I would like to mention that the fact that some measurements were taken by hand might be a potential source of error, as well as the presence of external electric fields from different objects in my room. Now, high-level summary of main results. I have calculated values for magnetic dipole moment and distance dependence factor, as well as the magnitudes of the net magnetic fields at 45 degrees obtained by both computational and experimental models. Continuing with the introduction, here are some of the main physical principles I used to complete this lab. PHYS event law, which relates the magnetic field to the magnetic moment, and the separation distance and distance dependence equation, used to calculate magnetic moment. Lastly, it is important to know that Earth also exerts magnetic field, and we need to isolate our biomagnet from it in order to collect accurate data for further calculations. The two main assumptions I made were 1. That the phone was moved in a similar manner each time, and 2. That the phone was perfectly aligned with the north. Now the experiment setup and measurements. First, we need to properly set up our smartphone in order to compensate for the magnetic north. Then I had to move my bar magnet to determine at what distance the mobile app records the values that we needed to measure. Full list of values is included in step 2 on this slide. I performed measurements 3 times and then took the average of these 3. After I did, I entered my values into the spreadsheet and calculated the distance dependence factor and magnitude of the magnetic moment. These calculations I will show in greater detail on the next slide. And finally, on the right side of the slide, you can see the table from Excel and the graph that I created using earlier discussed measurements. To calculate distance dependence factor n, we simply use the slope of the equation we derived in Excel, which we obtained to be approximately 3 as expected, because this implies that the magnetic field on the bar magnet is inversely proportional to the cubic distance. On the right side, we calculate magnetic moment mu. We set the Biot-Savart law equation to be equal to the distance dependence equation, where we obtain k by solving e to the power of negative 14.385. And finally solve for the magnetic moment to obtain 2.829 amps times meters squared. On the next slides, I have included lines of closed group code that I have edited to calculate B at 45 degrees. On the lines 12, 18, 19, 53, and 48, I included initial measurements, constants, and scales. On the lines 23 to 26, I calculate K and the magnetic dipole moment. Then on lines 34 through 38, I have function that calculates magnetic field due to a dipole at specific locations. Then we create 2 on-axis and 4 on perpendicular locations on lines 58 through 63. The next 3 blocks simply define magnetic field errors in each of the 6 locations. Last 2 blocks on this slide are for on-axis locations, and then this one big block shows the same process but for perpendicular locations. On line 112, I added the perp value obtained from the experiment, and finally, on lines 122 and through 126, I included the final steps of calculating and printing out the magnetic field at 45 degrees. Now let's compare the results obtained from experimental versus computational models. In the x directions on the experimental model, I obtained that 6.78 times 10 to the negative 6 teslas, and in the y direction, I had to correct the values by subtracting the value I measured for the Earth's magnetic field. So the magnitude of the magnetic field is 2.5 times 10 to the negative 6 Tesla. For the computational model, orange arrows represent on the axis magnetic field, blue arrows represent the perp axis magnetic field, and the purple arrow represents the off axis. We notice that these results are pretty close. In the computational model, we can also notice that on-axis magnetic field values are double the ones on perpendicular axis, which is what we expected as well. Finally, some reflection questions. Answering the first question, as I have mentioned on the very first slide, since Earth has its own magnetic field too, the results would just be less accurate since we would include Earth's magnetic field into our measurements. In answering the second question, if we put 2 magnets end to end, we would expect the magnetic field to be greater than with 1 magnet. We would approximately expect the magnitude of the B field to double. Thank you.